Hello everyone, I'm Jiayi Yang and I'm from University of Texas at Austin. I'm happy to introduce our paper, AlloyMC, Alloy Meets Model Counting. What is Alloy? Alloy is an open source language and analyzer for software modeling. Its applications include verification, security, synthesis, and so on. Its main workflow is like translating the Alloy specifications to set formulas and using its backend code solver to solve them and getting the final set solutions. One problem that the current version of Alloy has is that it's not efficient enough in getting the model counting result. What is model counting? Model counting is to calculate the number of solutions to a given set formula. Sometimes users only need to know this number, but don't need to know what each solution actually is. It has many applications, for example, to characterize properties of desired object graphs for bounded exhaustive testing, or to characterize properties of desired hardware litmus tests for finding hardware vulnerabilities. In a regional alloy, to get this number, we need to enumerate all the possible solutions and count the number, which will take a big amount of time. I also want to introduce the concept of projected model counting. Projected model counting is to compute the number of distinct solutions with respect to only a specific subset of variables. It has two main categories: approximate counting and exact counting. We selected two representative model counters for these two categories respectively. One is ProxyMC and another is ProgyMC. Note that AlloyMC is extensible so that other model counters can also be added in the future. For the major implementations, we extended Alloy grammar to include count commands, which will call the model counters in the backend. We also extended the grammar for the expect clause, which will make users better compare their expectations with the actual results. We updated Alloy GUI and added setting options for symmetry breaking level and available model counters. The current version of AlloyMC can be run on 3 mainstream operating systems without installing any other dependencies. Here is an example of AlloyMC GUI. In the coding area, we can list the Alloy model and count commands with expect clauses in multiple forms. In the log panel, we can see the messages and the detailed model counting results. I'd like to show the demo of AlloyMC with you. Before showing the demo, I want to first introduce the Alloy specification we used in our demo, the acyclic linked list. From the code, we can see that we used the Wenxi keyword to define the header for the list. Then we used SIG and fact keywords to define the set of nodes which are linked one by one from the header node. Then in the predicate acyclic, we made a requirement that each node shouldn't be reachable from itself following one or multiple traversals along the link. With the above settings, we can then define the acyclic linked list. Here is the demo. Hello everyone. Now I will show you the demo of AlloyMC. Note that since ProgyMC is not supported on our current operating system, the Mac OS, I'll only show you the usage and the final results of ProgyMC in this video. You can test ProgyMC on your Linux machine, and the whole procedure and the format of its final output is just similar to ProgyMC. So for the first step, we need to run the jar file which we downloaded from the GitHub repository in terminal. Note that the JDK version should be at least Java 9. Then the user interface will show up automatically. In the right log panel, we can show a warning that ProgyMC model counter does not work on this Mac platform. This is okay since we can still use AlloyMC as the counter. Now we can open the example Alloy model and test it. In the example Alloy model, there are 5 count commands in total. The first one is a default one without any expect clauses. The second one has a negative expected value, which will be ignored during its execution. The third one has an expected value in the form of A times B to C, and its default relational operator is equals, which means the user wants to check if the exact model count is equal to the count he gives. The south one has an extremely large expected value, which will exceed normal integer range. Our AlloyMC will handle it very well and gives us the correct results. The last one uses a larger than and equal to operator in the expect clause with a positive expected value. Other relational operators supported include equals, not equals, smaller than, larger than, and smaller than and equal to. In the options menu, we can select the symmetry breaking degree and the counter we want to use. Now we'll just use the default ones, the symmetry breaking degree of 20 and the AlloyMC counter. In the execute menu, we can run each command respectively or run them together. Note that since the second command has a negative expected value, its expect clause will just be ignored during the execution, so it is just the same as the first default count command. Now let me run these commands one by one. Now let me run them together. We can see the model counting results in the right log panel. We can take a look at a specific command's output. Say the last command. The model counting results include the parameters of the set formula, the time used by CNF set solver, the exact model count, and the specific symmetry breaking degree, a hyperlink to the full counting results, and the time used by the counter. When we press the hyperlink, the full model counting results will be shown in a text window. Sometimes, the execution time of counting may be too long for the users. They can also choose to stop the model counting process and run some other commands. So now we add a count command, count cyclic of 50. This new command will take a much longer time than the default command count is cyclic for 5. When we press execute, we can see that it takes a little bit longer to generate the CNF, and for the counting process, it will take even longer time. So the users can now press the stop button. And the model counting process will then be stopped. The users can now run some other commands he wants to run. That's all the content of the demo. Thank you for watching. Thank you for watching the demo. Besides this, we also did a series of experiments on 10 classic Alloy models to test its model counting efficiency. From this chart, we can see that we can get the results of most of the alloy models within our time limit of 60 seconds. Here are the detailed results. We have 14 predicates from 10 alloy models. By applying both the AlloyMC and the ProgyMC on these 14 predicates, we got 6 10-mod results in total. Even for a case where the model count is super large, say some set predicate in messaging specification, the two counters can still get the results within the time limit. Also, it is infeasible to get these results in such short time by solution enumeration in original alloy. That's it. Thank you for listening. We are looking forward to any questions you may have.